Okay, I wanted to continue off of the previous video. If you remember where we ended there, we were talking about a general smooth curve, and I showed this, that the instantaneous rate of change of position of points on that smooth curve relative to arc length turned out to be what we were calling the unit tangent vector. So t hat, in this case, parameterized by s, okay? But we can think about t hat in general. By the way, this parameterization in terms of s for a curve is nice in theory, but often it's quite difficult to actually work with, because if you remember from Calc 2, for example, you remember that actually computing arc lengths could be quite a problem. You ended up with some really ugly integrals in many cases. But along lines and circles, it's actually quite easy. And in general, it's a good theoretical tool. Okay, so that's the way we're going to think about it. But you want to remember this in this box here. The instantaneous rate of position of points on a smooth curve relative to arc length is going to be t hat. Okay, unit tangent vector pointing in the direction of increasing s. Alrighty? Alrighty. Okay, we're going to define something here called curvature. Okay? Now, the curvature is going to be a measure of how curved the curve is, okay, that you might be dealing with. Okay? And we'll show you what we mean precisely by that here in a minute. Let's do this. I'm going to just play a little game here for a second before I define curvature. Now, I'm going to use s as my parameter here. Okay? Now, t hat of s dotted with t hat of s should be what? You remember the dot product of a vector with itself is what? The square of the magnitude of that vector. Okay? But since I have a hat on here, that's a unit tangent vector, its magnitude is always 1. So I've got t hat dotted with t hat equaling 1 for all s, not just for some s, for all s. Okay? Now, I'm going to play a little trick here. I'm going to differentiate both sides of this identity, is actually what it is, with respect to s. Okay? With respect to that arc length. So that we're using as our parameter. So I would do that on both sides. And here you remember that with the dot product, and in fact with the cross product, we've got what? We've got a product rule going on, just like in Calc 1 here. Okay? But you have to remember the product is a dot. Okay? So this says if I'm going to differentiate this way, I'm going to have what? The derivative of the first times the second plus what? The first times the derivative of the second function here. Okay? All right? In this case, these functions are vector valued here, so I get what? T hat prime of s dotted with t, right? Plus t dotted with t prime. The derivative of 1 is always 0, so we've got this as an identity also. This holds for all s up here also. Okay? Now, unlike the cross product, the dot product is in fact commutative, so that we've actually got, we can change the order of the product here. And we see we've actually got two of these, t prime dotted with t. So two of those is going to be equal to 0 for all s. That means dividing both sides by 2. T prime dotted with what? T is always 0. Okay, that may mean for all s. What does that mean? That means t prime of s and t of s are orthogonal, or it could be, since this is a unit vector, this is never going to be 0 here. Okay? It could be that that is going to be what? That could be 0. So these are either orthogonal or that guy right there is 0. Okay? And some people would say in a degenerate way that makes them orthogonal too. However you want to say it. Alrighty? So let's keep that in mind here. Now I'm going to come over here. Remember what I just did was what? I differentiated t hat with respect to s. What we're going to do here is create a little definition here, essentially. The instantaneous rate of change of t hat with respect to arc length, I'm going to say is equal to a certain vector, kappa times n hat. Now let me explain what kappa is. Oh yeah, that's a kappa, not a k. That's a Greek k. Okay, so this is actually supposed to be a kappa. It looks essentially like a k. The book has it printed better than I do. But anyway, this little kappa is the magnitude of dt over ds, okay, and we call this thing curvature. And we'll explain why we would say that here, and it expresses the curviness of the curve here. Okay, well, you see here, well, on this side, let's come back up here. You see I've got this vector, and then if I imagine dividing by its own magnitude, assuming it's not zero, if I divide that by its own magnitude, which is in this case kappa, you could see what I would end up with was what? A unit vector here. And I'm going to give that a name. I'll call it the principal unit normal. Okay, so I could write this. dt over ds equals kappa times n hat. Okay, this thing is called the principal unit normal, and this is going to be our definition here. Now let's discuss just a little bit before about the principal unit normal. Let's talk about this whole idea of curvature. Okay, think of this, the instantaneous rate of change of t hat, the unit tangent vector, with respect to arc length. Okay, so if I've got some curve here, just kind of, all right, it's supposed to be smooth, but you use your imagination. Okay, and I've got a unit tangent here, okay, and I've got a unit tangent here at a point close by. Now these are both unit tangents, right? These are both t hats, okay? If I travel just a small distance here, you can see I didn't really change direction very much. Think of t hat as being what? The direction in which the curve is pointing at each point on the curve, okay? If this doesn't change much, it can't be very curved, right? If this doesn't change very much, then it isn't very curved here. Oh, I should mention here, because it's a magnitude, the curvature is always going to be greater than or equal to 0. Okay, so kappa is always non-negative. Okay, but this is talking about how quickly you're changing direction when you move, what, a short distance here, okay, along the curve. Now, you can see here, for example, can you guess this? Suppose this is, all right, it doesn't look straight, but suppose that was a straight line. What's the curvature at each point on the curve, do you think? Well, you can think about what? The unit tangent vector to each point on the curve, there's no change, right? So in fact, the curvature of a straight line is 0 at each point on the line. Okay, it's always 0. On the other hand, if you've got a curve like this, let's say, try to get the idea here, you know, it's really tight here. Do you see this is changing direction very quickly? So this is a unit tangent vector just showing direction. Okay, and I come here. Do you see this is pretty curved? You know, if I take some point here, I would actually have to take the limit as the change in arc length goes. But you get the idea here. I don't have to move very far, right, along the curve, and I'm really changing direction quickly, right? So you would say something like this: the curvature at this particular point that I'm xing right now is large, okay? So a tiny little circle is going to have a very great curvature, but a great big circle is going to have, all right, well, this is part of a very big circle, is going to have a very small curvature, all right? All right. Now, think for a second here. What do you think is true here? Can you name curves that have constant curvature? Okay, curves of constant curvature. Well, a straight line has constant curvature 0. Can you think of a what? A curve which has a constant curvature that's positive? Okay. Well, we're going to show here. We're going to create formulas for this. I mean, this is just definition right now. It's not a very useful formula. But it's actually circles. Circles are curves of constant curvature. Okay? Constant curvature. Now, this thing about the principal unit normal, let's talk about that in there. Let's throw this in here. You know, let's take this curve that I've drawn here. Yeah, let's maybe draw another one instead. Okay, let's say I've got a curve here, and I've got the unit tangent vector here, so that has length 1, right? Just showing direction. Okay, the principal unit normal is always going to be pointed inside, so it's going to be towards the inside of the curvature. So this is going to be our principal unit normal. Okay, principal unit normal. These are always going to be what? Orthogonal. Those are going to be orthogonal to each other. Okay, you see I've got that written right here. That follows from the arguments up here. Okay, remember this is essentially what? What isn't essentially? It absolutely is. This is that thing right there. That's kappa in hat. So n hat dotted with t hat is going to be 0. These are orthogonal to each other. Okay, in the case of a straight line, there really is no n hat though. Okay, t is just pointing this way. You can see here, there's no curvature at all. There is no n hat. Okay, but that's only going to happen when the curvature is 0 here. That's the only time you'd have to worry. That's the only time this doesn't exist here. Okay, well, that's the idea of curvature. How quickly is the unit tangent vector changing with respect to what? Arc length. Is it really changing direction quickly, or is it changing direction slowly and gently? Okay, that's the idea of curvature. Okay.